So, hi everyone. Today we'll explore tools and techniques for evaluating regression models beyond just linear regression. As we saw last week, regression models predict values based on factors. However, there are some challenges. Linear assumptions, model may assume a straight line relationship which isn't always true. Multicollinearity, highly correlated features can make the model unstable. Overfitting, complex models may not generalize well new data. And sensitive to outliers, extreme values can distort prediction. That's why we'll learn to evaluate regression models using mean absolute error and root mean squared error. We'll also cover recursive feature elimination to choose the most important features for your model. Lastly, we'll compare models like random forest to predict customer spending habits and see which one works best. By the end, we will know how to evaluate and choose the right model for your data. Evaluating the accuracy of a regression model. To evaluate regression models, it's important to use specific metrics that measure how well the model makes predictions. These metrics are based on the concepts of residuals and errors, which indicate how much the model's predictions differ from the actual values. In this section, will first explain what residuals and errors are. Then we'll introduce two key evaluation metrics, mean absolute error and root mean error, and show how they help assess the accuracy of regression models.
So, residuals are the heart of understanding how well a regression model performs. A residual is the difference between the actual value and the predicted value. Residuals help us estimate the error in a model. While we can't know the exact error because the true process generating the data is unknown, residuals provide a close approximation. Let's take a practical example from the book. So the table below shows the actual selling price of item and the price predicted by a machine learning model in Indian rupees. If we sum up all these residuals, we get 0. So at the first glance, this might make it like the model is performing perfectly, but that's not true. Looking at the residuals, we can see that the model is consistently missing predictions by a large amount, either overestimating or underestimating. And the problem is that positive and negative residuals cancel each other out when averaged, which gives us a false impression of accuracy. This is why we don't use raw residual as a metric. So now, why are residual important? So by analyzing residuals across all predictions, we can calculate evaluation metrics like MAE and RMSE. These metrics summarize the performance of model and allow us to compare it to other models. So for example, a model with a smaller residual will have a lower MAE and RMSE, indicating a better accuracy. So in summary, residuals are essential for understanding a model prediction quality, and also they form the basis for all evaluation metrics that we will discuss next. So the mean absolute error, or MAE, is one of the simplest and most commonly used metrics for evaluating regression models. It calculates the average magnitude of residuals, ignoring whether they are positive or negative. So let me give you an example. Imagine you are predicting sales for 5 stores. The residuals for these predictions are 1,000, 2,000, 500, and 3,000 and 1,500. To calculate the MAE, we first take the absolute value of each residuals to get rid of the negative signs. Then we add them up, which give us 8,000. And finally, we divided this sum by the number of prediction, which is 5. So the result is 1.6 thousand. And this is the average error that we can expect from the model. MAE is intuitive and easy to understand. A smaller MAE means the model is making more accurate predictions on average. However, there is one limitation. MAE treats all errors equally, regardless of their size. In some cases, larger error may have a more significant impact, which MAE doesn't account for. This is where the RMSE comes in, which we will discuss next.
So now about the root mean squared error, what is this? It's similar to MAE, but the key difference is that it squares the errors before averaging them, and then takes the square root. This means it gives more weight to larger errors. So here this is the formula. And then why is RMSE useful? If your model has a few big mistakes, RMSE will show a higher value because those big errors are emphasized. So it is useful when you want to prioritize reducing large errors. Here it is a visual example for the book, where we can see that as the size of the error increases, the squared errors grows much faster than the absolute error. So it helps us identify and prioritize the most significant mistakes to avoid. So here we did an exercise for evaluating regression models using the MAE and RMSE. So here are all the codes and the results. Then so here this is the interpretation of the results. In this exercise, we evaluated regression models using the MAE and RMSE, as I said. From these results, we observe that the first RMSE is higher than MAE, indicating large errors are affecting the model more. And then we can see that both RMSE and MAE increase, meaning the model's errors are getting worse. In short, RMSE is always higher than MAE, showing that big errors are having a stronger impact on the model's performance. So the key is to reduce the large errors that are causing RMSE to be much higher than MAE.
So now let's talk about the activity. So we used the regression evaluation metrics to analyze customer responses to a marketing campaign. And the objective of this activity is to identify which variables, out of several possible factors, are the most important predictors of customer behavior. So imagine a company has run a marketing campaign offering discounts on various products. They collected data on offer discount, the size of the discount provided in each campaign, offer reach, the number of customers who saw the offer, and also offer quality. That is a subjective score assigned by a marketing team reflecting their perception on how appealing the offer is. So the task is to figure out which of these variables are essentials for predicting the numbers of customers' responses to the offer. So why it is important? Because understanding the key drivers of customers' responses helps the company design more effective campaigns while avoiding unnecessary complexity in their models. So to solve this, we build a multiple regression model and evaluate their performance using RMSE. So first we build the full model, and then we removed one variable at a time to see how it impacts the model accuracy. So for example, we can see the interpretation on the next slide. So when we removed the offer quality, the RMSE changed only slightly compared to the full model. And this suggests that the offer quality, while somewhat important, doesn't have a significant impact on this customer response. And on the other hand, removing offer discount led to a noticeable increase in RMSE, indicating that it is an important variable for understanding customer behavior.
So now I'm going to explain to you all what recursive feature elimination is. So basically, it's a method to figure out which parts of your data are the most important for making predictions while getting rid of the useless ones. So when building models, selecting the right features is crucial because throwing in all the data you have might lead to problems. So some of the data could be irrelevant or even harmful to your model's performance. For instance, if your dataset includes random details like the store's manager middle name, that's not going to help predict sales. It's just noise. So in other words, RFE helps you pick only the most important pieces of data, which are called features, to use in your model. So this not only makes your prediction more accurate, but also faster and easier to interpret. So how does RFE work? So RFE is a step-by-step process. So first, it starts by training a model, like a linear regression, on your entire dataset. Then it identifies the least important feature and removes it. And finally, this process repeats until you're left with a specified number of features. By removing irrelevant or redundant features, RFE helps your model focus on what really matters, so preventing overfitting and improving performance on unseen data. So now I'm going to explain the steps for using RFE. So first, you import RFE from the scikit-learn package. Next, you create an RFE instance, specifying how many features you want to select. Then you feed the RFE model on the training dataset. After that, you can find out which columns were selected by RFE. Once you've completed these steps, you will get the following output here that you can see here in the bottom. So then I'm going to show two ways to use RFE through exercise. So the first exercise, it was to using RFE for feature selection. So it was a few simple steps. So we can show you at the end on Google Colab. But first, to explain how it works, so we loaded the data from 20 scores.csv, separated the target variable y, which is the revenue, and the predictor variables x, which are the 20 features that you can see here. Then we split the data into training and testing sets to train the model and test its performance. Next, we used linear regression as our baseline model. This model used all 20 features, and we calculated the RMSE to measure its performance. This RMSE acts as our baseline for comparison. Then we applied RFE. We set it to select the 5 most important features by testing and removing the least useful ones step by step. After running RFE, we printed it, the selected features and their ranks. For example, it selected feature 0 and feature 9 as the most important one. For example, here, the RMSE model of the reduced model was slightly better than the baseline, showing that RFE improved the model while making it simpler and easier to understand. So here, RFE helps us focus on what really matters in the data, reducing complexity without losing accuracy. And for the other exercise, it was using RFE to predict customer spends. So really, we investigated which factors influence customer spending in the current year. So the dataset includes features like previous year spend, days since last purchase, total transactions, income, and more. So our goal was to find the 3 most important features using RFE and then build a simple linear regression model. So first, we loaded the data from customer spends and inspected the first few rows to understand its structure. Next, we split the data into training and testing sets using the current year spend as the target variable and the other columns as predictors. We then applied RFE to identify the 3 most important features. So RFE works by testing each feature's importance and selecting the ones that contribute the most to predicting customer spend. So for example, RFE might select a previous year spend, the income, and the engagement score as the top features. After identifying the key features, we created a reduced dataset and trained a linear regression model on it. So finally, we calculated the RMSE for this reduced model. So the RMSE was approximately 1075.91. So this score is showing that the model remains accurate while being simpler and faster to compute. So here it shows that RFE simplifies our model by focusing on the most relevant features, making it easier to interpret and just as effective for prediction.
Let's now explain what is the tree-based regression model. You all know that linear models are not the only type of regression models. Another powerful technique is the use of regression trees. Regression trees are based on the idea of a decision tree. Imagine you're trying to predict how much a customer might spend based on their age or income. If you drew a straight line through the data to make prediction like in the first graph, you might miss some important patterns. That's where the tree-based regression models comes in. These models break data into smaller groups or branches, like a decision tree. At each step, you ask whether a variable is greater than or less than some value. Each answer splits the data into smaller and smaller groups until the model has enough information to make a prediction. The final predictions are made at the leaves of the tree, which represent the smallest group of data. Let's take an example. If you want to predict the age of a person with a height of 1.7 meter and a weight of 80 kilo, let's use the regression tree. On the left part of the regression tree, because the height is less than 1.85 meters, so we follow the left branch. Similarly, since the weight is less than 90 kilo, you will follow the left branch and end at 18 years old. That means that the age of the person is 18 years. How to apply it to coding. When adding a tree-based regression to code like in Google Colab, you will simply need to import decision tree regressor instead of importing linear regression, as shown here. When coding, a key parameter for regression trees is the maximum depth of the tree. The more depth that a tree is allowed, the more complex a relationship it can model. While this may sound like a good thing, choosing too high a maximum depth can lead to a model that is highly overfitted to the data. Being overfitted to the data, meaning being too specific to the data they were trained on, and then they don't work too well for the new data. In fact, this tendency to overfit the data is one of the biggest drawbacks of regression trees. That's where random forests come in handy. To fix the issue of overfitting, we use a more advanced version called random forest. Instead of building just one tree, random forest builds hundreds of trees. Each tree looks at slightly different part of the data, and their predictions are combined, taking the mean or the average of all the trees. This makes the model more reliable and less likely to overfit. How to apply it to coding? First, you need to import the random forest regressor from the sklearn module. And in the following code, you can change the maximum depth of the tree present in the random forest as per your requirement. When should we use a random forest? Tree-based regression models are especially helpful in marketing when either you're analyzing customer behavior that's more complex and not linear, like how income and weekend shopping patterns could affect sales. Or either you want to explain decision clearly to stakeholders, as the tree structure is really easy to interpret. Now it's time to put the skills we learned to use by doing a practical example. In this exercise, we want to figure out how spending habits change with age in our customers, and how well different models capture this relationship. To realize this exercise, we imported different data from the book, including the customer's age, taste, the train split, pandas, RMSE, etc. After adding all the line of code into Google Colab, we added the decision tree regressor and chose the depth of our tree. What are the results of the coding? You can see that the linear regression model just shows a flat line across the ages in the first graph. It was unable to capture the fact that people aged around 40 spend more, while people younger and older than 40 spend less. The second result, with 2 layers of 3, does a better job of capturing the relationship, though it does not capture the sharp decline in the oldest or youngest population. The last result, with a maximum depth of 5, does an even better job of capturing the relationship, properly capturing a sharp decline in the oldest or the youngest population. Now, if we apply the method of random forest we just explained, we get an even more detailed prediction like in the first graph. To sum up, we just saw that the tree-based models outperformed the linear regression model since the data was non-linear. Among the tree-based model, the random forest model has the lowest RMSE value. We also saw that by increasing the maximum depth from 2 to 5, the curve started fitting the training dataset more tightly.
So to conclude, evaluating regression models is more than a technical step. It is the foundation of trust in your prediction. Through metrics like MAE, RMSE, and R-squared, we quantify how well our model performs, offering insights into their accuracy, visual tools such as residual plot, revealing hidden error, ensuring our model that are not just functional but optimized for real-world scenarios. Beyond evaluation, advanced techniques like recursive features elimination, RFE, simplify models by focusing on the most impactful variable, while methods like random forest regression handle complex, nonlinear patterns that our traditional approaches might miss. Together, these tools not only improve the prediction of our models, but also make them robust enough to handle new and unseen data.